Can it be even? Can you make it full screen? This is okay. You have your thing. Oh, Madhukar is here. Good.
Yeah, hi sir. Can you hear me?
Yeah, I can hear you.
Okay.
I thought it would be nice if Guhan was here because it's on explainability. I don't know.
Yeah, but I thought he had classes today from 1 to 5.
No, but he usually attends on Thursdays.
Oh, is it? Oh, then I think this was one of the classes that he was talking about.
Ah, it's too bad. And we're also missing a few folks here. Usually I have full attendance
Okay.
from
Yeah.
here because I gave them an ultimatum.
Okay.
That
Yeah.
it worked till today, so I'm not sure.
Yeah. So was there an email today? I didn't get any.
No, I didn't send an email today, man. I mean, I sent one yesterday.
Yeah.
I didn't feel like I had to send one today.
Yeah, no, I agree. Yeah.
I mean, as is, people can arrest me for spamming. Okay. I don't know if there are laws against spamming.
Yeah.
Are there laws against spamming? I guess too much spamming can be considered as being harassment. And they
Yeah.
arrest you. Do you think there are laws against spamming?
I don't think there are any, but
Oh well, it's 3:35. Shauriyam said that he was going to be here when I gave him a thing, and he's not here.
so
There is a group, no? Why don't you send him a message on the group, man? Hmm?
so online there are only
No,
three.
online only you. Even Diganta said that. கொஞ்சம் இது வருது இல்ல சரி நான் மியூட் பண்றேன் அப்ப நான் பேசணும் என்ன இதுல பேசணும் அதுல பேசினா போதுமா hello Madhukar, can you hear me?
Yeah, it was a little the voice was not as strong as it was
Can you
earlier.
hear me now?
Yeah.
Okay. Jessica. Hey, Shankar. Oh. Always a problem. He just disappears. He's so busy. There's still this feedback, huh? Yeah, I still see feedback. I think we should start.
So
Please go ahead.
yeah, so I'll start now. Is this audible? Like, okay.
It's okay for me.
This is okay. Okay. This is okay, no? Okay. So, so the paper is about formally approximate minimal explanations of neural networks.
Avika, I can't hear you. I'm not sure if you're speaking.
No, nobody's speaking now,
Okay.
but there is a bit of an echo. Madhukar, can you hear me now?
Yeah, I can hear you, sir.
Okay. So then it works. Fine. Speak.
Hello.
Yeah.
Is it
You're
okay?
okay.
Yeah, I can hear you.
Yeah, okay. So, so the paper is about formally approximate minimal explanations of neural networks. So there's a lot of technical things involved. We'll see what those terms mean. So this is the presentation overview. We'll see what explainability is and
Warning you. There's going to be a lot of technical things. So
yeah, so you need to pay attention. Yeah, and you can ask whatever you want in detail. So yeah, this is the overview. We'll see explainability and the need for it, and like various approaches which have come up recently to achieve it. And of course, there are limitations to that. And we'll formalize the notion, and we'll see algorithms to compute the explanations which are provably correct in this paper. That's the crux of this paper actually. And we'll see methods to optimize those algorithms because they'll be slow. We'll see that. And we'll slightly touch upon how to make the explanations more compact using a notion called bundles. And we'll see experimental results and comparisons. So, okay, so what's the need for formal explainability? Well, we know that DNNs are black boxes, so it's quite incomprehensible to humans, especially the internal structure. It involves a lots of nodes and everything. So we're not really sure why a certain output class is predicted by the DNN on a given input. So it's very prone to adversarial attacks in that sense. So yeah, this is what we'll want to know actually. So why for a given input, an output class is predicted by the DNN. And so for this, explainable AI has recently come up, which tries to construct models for explaining those outputs or classes and interpreting the decisions of the DNNs. So yeah, so work today has focused on heuristic approaches, but they may not be that much reliable because you can't really prove them logically. Like they are some kind of estimation, but yeah, they are informal explanations. So we're not sure about the correctness and succinctness which we want. So succinctness just means that the explanation is very compact without wasting any words. So formal DNN's explanations promises to give such provable guarantees for the explanation. So you can logically work it out. So recent approaches to achieve this was like by the FB community to get some formal and rigorous explanations for a DNN have been tried out. And this is one of those approaches. So yeah, many of these approaches actually rely on something called as DNN verification, which we are actually familiar of, but you'll know when I say it formally. And so these approaches typically produce an abductive explanation, so or a prime implicant. Basically, the sense of abductive here is that the explanation is kind of some subset of the features, input features that we feed to the DNN, the input nodes, and a subset of that thing, which forces the output class to be certain, a certain class. So that's the sense of abductive here, and we'll see why it is so. So first, let's discuss the advantages and disadvantages of this approach. So advantages would be what we started with, that it provides us formal guarantees that our thing is correct, actually, provably correct. And it can give simple, comprehensive explanations as to why a certain class is what it is, given a certain input. But there are disadvantages, which is the first and foremost is the scalability. We'll see that the algorithm that we use here incurs quite costly and expensive calls to SAT solvers, and it's expensive, and as the search space grows exponentially, we'll see that. And it could be exponential in many worst cases. And there could be varying preference among the users. Like some users, because this is an explanation which is solely based on input features, but some users may not like it. They might want some high level explanations which are not solely based on this input features, but something extra also, maybe the working of the DNN itself or the structure of the DNN itself. But this approach doesn't depend on those things. So some users may not prefer this. Yeah. So so tackling these two problems, what we'll do is we will try to minimize those problems. So we'll try new approaches to efficiently produce this kind of explanation, various approaches. And yeah, and for the preference limitation thing, we'll try these bundles as we discussed, which kind of gives a more compact, more sensible explanation. And we'll see with an example how. So let's get into formalizing all those notions. And here in this paper, they have exclusively used the DNN as a classifier, which takes certain features. The input nodes correspond to features, and the output nodes correspond to different labels or classes. They've used only this in this paper. So a DNN verification, which I mentioned earlier, is a tuple P and Q, where n is the DNN that maps the given input vector to an output vector, basically to a class. And we denote it by the output vector y is just n of x, predicted by the DNN. And P is a predicate that depends on x, which is the post condition. P is the post condition, and Q is the
is a precondition. Yeah.
Oh, sorry. Yeah, sorry. It's a predicate, it's a precondition, and Q is the post condition. So, and Q depends on Y, which is the output predicted by the DNN on X. So, yeah, a DNN verifier will need to check the satisfiability of this formula. If there exists such an input X0 for this, this conjunction is satisfied, which is both the pre and post conditions are satisfied. SAT case is for satisfiability. Unsat case, as we know, we want to check for validity, so we take the negation and check for unsat. And in general, this verification problem is NP complete because the variables can take like exponentially many values. So a classification problem is this four tuple FDKN, where F is just the set of features. So here we have considered M features. It could be any number, and so these DIs are the domains of each feature. So feature 1 can take its value from DI. For example, feature 1 could be color, and its domain would be, let's say, blue, black, white, whatever. It can take values from that domain. And similarly for each of those. And K is the set of classes or labels. So each class actually corresponds to each output node of the DNN, right? So yeah, these are the set of classes, and yeah, these are the input nodes. There are M input nodes, so each feature corresponds to an input node. And N is just the DNN which takes an input. This capital F is the input space, which takes this M vector and it gives a class as a output. Yeah, and this is the input space, which is just the cross product of this thing, an M vector basically. What?
Is 0, 1.
You mean this thing? No, not necessarily. It could be any features. I mean, it could be 0, 1, but it could take any value. Like, yeah, it depends on the feature.
Yeah, he will show an example. But for example, one D could be positions of the.
Yeah.
Or it could be some finite discrete things like grayscale values of each of the pixels.
Right. So that feature can take multiple values. Those values are in the set DI. So yeah, and the classification instance is just a pair V, C, where V is our input vector, and for that input vector, whatever the DNN predicts, that is C. Yeah, so V belongs to the input space and C belongs to the class set where C is N of V basically. And we'll see an informal overview of an explanation first before going into the formal definition. So for a given classification instance V, C, so we already have a classification instance. The DNN has output something. Now we wish to know why this C particularly has been output by the DNN on this given input vector V. That's what translates into asking an explanation for this classification. which we want to answer. So informally, an explanation is just a subset of the features.
I think I want to interject here. So explanation, you did make this point, so I want to re-emphasize. So the explanation is defined with respect to a particular classification instance. Okay, there could be other notions of explanations that other papers might, introduce, and you will see that the next paper that Guhan will be presenting will use, quite a different notion of explanation. So there could be different notions of explanation, but here it is trying to explain why a particular value is being classified as C.
Yeah. So yeah, informally, it's just a subset of the features. Basically, we had that feature set 1 to M. It's just a subset of that thing, so that as soon as you assign the values to those features in E, the same values as this V, it will automatically be classified as this output class C. So let's say you have like 4 features, and an explanation could be the first and the second one. So as soon as you assign the first and second value to that value which is in V, then the remaining features don't matter. The third and fourth don't matter. You can change them arbitrarily, but the DNN will still classify them as C. So the subsets kind of forces the output to be this class C. That's what it informally means. So we'll see it formally. It will be more clear. So this is an example from the paper. So this is an image. This has been taken from the, I think, MNIST fashion dataset, and this is supposedly to be output as a shoe. So the feature set could be the positions, the positions of each pixel, and the colors black, blue, and white, which that pixel particularly has. And an explanation could be a critical subset of these feature sets. In this example, you can see this is the subset, like the blue ones, the non-white ones are actually in the explanation. So those pixels actually matter here, because as soon as you give values to this particular form, these pixels here don't matter. So that's the sense actually. These white pixels here don't actually matter. As soon as you give this kind of shoe layer, it will predict it as a shoe. So that's why this is an explanation for this. And of course, this is an approximate one. So we'll see that. Yeah, so that's why there may be noise also, but yeah.
Just pause here. So is that informal view clear? Yeah. Okay. Now, yes.
Yeah.
Yeah. So if you go to the slide before, when you said about E,
yeah,
the E can be, whatever the subset can be different for different inputs.
No, because your inputs are just this M tuple, right? So your inputs, all inputs are basically features. They're not values actually. Sorry, the feature is a value, but an input particularly assigns some value to each feature.
So basically, you're saying you're trying to identify the important features from
Yeah.
the feature vector.
Yeah, exactly.
So
Which actually matters.
How is this different from things like dimensionality reduction? Like even there you're
dimensionality reduction.
So let's say you have a feature vector of 256 vector features.
Yeah.
And let's say you want to reduce it into trying to, you're reducing the dimension of the feature vector.
Okay, yeah.
Things like PCA.
Yeah.
So they try to reduce the input size without compromising too much on the output. So,
yeah, no, but the thing is, in this paper, like they are trying to explain that thing actually, like why the DNN works.
It is maybe they're trying to design it such that they can optimize it too, so that you can throw away redundant information in the thing. But here, once you've designed, you're trying to analyze for any particular way of classifying it, why it is behaving like that and so on.
And this is for a particular instance, right? So if you change the instance, the explanation will change.
Different.
Yeah. No, an explanation, a classification instance is just a particular input vector and a class corresponding to that is output by the DNN. That's a particular classification instance. Yeah. If you change the instance, let's say you have changed the classification instance, you're taking some other vector now. Yeah. Yeah. So then the explanation would change. Yeah. Yeah. It
Does
depends on.
depend the input. So
Yeah, it actually depends on the classification instance that you're taking. Yeah, because explanation is for a particular instance. Yeah. Okay. So yeah. So now we go on to the formal definition of an explanation. So this is a given input. So V1 just here means the value of feature 1 for this particular input. Similarly, VM.
So, Avik, Madhukar here, I have a question.
Oh, okay.
yeah, Madhukar?
Yeah.
Yes.
Yeah. So this one, so the image that we saw earlier, that of a shoe, and we saw the kind of the important input neurons were taking a similar shape, right? That's what you were trying to show there, right?
Yes.
Yeah. So I mean, I was wondering, is it always the case, right? I mean, suppose if you're looking at digits, let's say that if you're trying to, I mean, IST has this digit data set, right?
Yeah.
Now, if we look at why is a one a one, if we try to explain why certain images are being classified as 1 or 2 or 3, will we see that a similar shape as that of a 1, that's saying that these neurons are important and that's why it is being classified as a 1? I mean, do you see it happening more often than just for the shoe case? Is what I was trying to understand. Is that a general thing, or was that a peculiar example? Or do you understand my question?
Yeah, let me.
No, I'm not sure.
Okay, let me try to understand. I think let me try to understand. So will the explanations, if for a digit, as Avik pointed out, this notion of explanation is limited to explaining a particular classifying instance, okay? So if the network is supposed to recognize, like in your case, digits, okay? When it recognizes 1, okay, so there might be several different inputs for which it may recognize each of which it may recognize as 1, okay?
Correct.
Now, what here they're limiting themselves to that notion. So if when it recognizes as 1, what subsets of the features in the input are significant to classify this as 1, okay?
Yeah.
As opposed to, suppose, okay, so there might be some bordering or some certain features of the input itself that, so, certain pixels may not matter. There is always some pixels that matter. I mean, as an instance, I'm saying. So your explanation for the shoe will be different from an explanation for a 1.
Yeah, right.
Correct. But what I was asking is that, the explanation for a shoe looks, the shape of that explanation looks similar to that of the shoe that we are trying to explain, right?
Say that again. The explanation for a
for that shoe was, the shape was looking similar to that, right? So the neurons that were important were kind of taking the same shape as that shoe.
No. I think the explanation will be, so there is some, bordering pixels, okay, that are critical. Okay, the explanation will be, look, there are these, border where the pixel changes from blue to something else, okay, and those positions, the color of those things are important, okay. So all the rest are unimportant, okay? And even the ones, like there are some whites inside the shoe, even that are not important. So the distinguishing features, which in this case is some positions or relative positions of all these pixels, and what the color that they take, are what are important in classifying this thing. So if you had some noise, if you made that blacks or all or whites, it wouldn't matter. Okay.
Yeah.
That is the kind of explanation, a kind of example that this would give. This is trying to analyze and
Yeah, for example,
explain.
like here, if you make changes to these pixels, maybe you color them black or blue, it won't actually matter. It will still predict as a shoe. So these pixels here actually don't matter. So that's why they are not included in the explanation for this particular instance. Yeah. So
Okay.
that's the idea.
Sure.
Is it clear? So
Yeah, sure.
okay. Yeah. So
Yeah, I think I understand the import of you, Madhukar. Okay, this may not always be appropriate, okay, for all kinds of explanations, okay.
Yeah.
Even for the shoe example, I mean, I looked at when I read the paper, go back to the shoe example, it's kind of critical. See, if you just make all the black pixels here blue, then it probably won't recognize it as a shoe. Okay, what is critical is that there must be this pixels that form the border. Okay,
Correct.
where it changes from blue to non-blue. Okay, that is critical. Those two things, and then it doesn't matter. All the rest won't matter, and even probably the ones inside, those pixels inside, won't matter. That could be why it does that. Okay, so that is the kind of explanation that this thing gives. Okay,
Correct.
yeah. So like in the inside, there should be some crowding here because it should give the sense of this shoe. Can't be completely empty then. Yeah. So that's why. It's a boundary which is kind of filled up with some stuff inside.
Correct. So the question that I was actually asking is that suppose you had this black background and you had a white 1 written.
say that again. Why?
So you had this black background with like the one on the left. Okay, so you had a black background and you had this numeric 1 written in white color.
Okay, yeah.
Okay, then a similar explanation for that, that 1 being classified as a 1, would it look similar to that 1 in the outline? That's what I was asking. That do you imagine this being a more generic thing, or is this only a peculiar behavior that here also?
No, I think here. Oh, so you're saying, if I understand your question correctly, what happens if there was a white 1 written in the black portion to the left? Yeah, is that what you're saying?
I'm saying that forget the shoes. I imagine that the entire thing is black, and suppose there is a white 1, like the blue shoe. There's a white numeric 1 or a blue numeric 1.
Yeah.
Then the explanation for that, on the right, would it look similar to that 1 in shape?
No, or it would be different. So it would be, once again, if it recognized it as a 1,
correct,
then the subset of the features will be different. Okay, so maybe the location of the positions of the pixels that need to have a white value could be, so it's just that subset of the input, pixels that conform to the shape of what is close to 1 is what will be, it'll say that is significant. If I change those pixels, those white pixels that are, if I change that, it'll misclassify. That is the kind.
Sure. Yeah. Thanks, sir. Yeah, you can carry
on. So this is so as I was saying, this is a given input, like it has particular values. So V1 has some value from D1 and so on. And the output class for this is C. So an explanation is a subset of the features such that for any input, for any vector from the input space, you set those values in this indiced in this set E, the same as this V. So let's say it was like V1, V2, V3 only. Like the E had only 1, 2, and 3. Let's say, for example. So as soon as you set X1 to V1, X2 to V2, and X3 to V3, it will all, classify it as C. The remaining like M-3 features won't matter. The X4 and so on won't actually matter. So that's actually the formal sense of it. Like, is this clear definition?
Yeah, this is very important for you
Yeah.
to understand. So two things. One is the E is not values; they are actually indices.
Yeah, they are
okay,
indices.
for the features. That is one important thing. And then you're setting the values at those, for those features the same as your input. Okay, the rest could be
Anything.
whatever, okay,
Yeah.
arbitrary. That it would still give it a C. Yeah, yeah. So Sulagna has a question, sir.
So we are extracting out those xi's like equating to vi's. I mean that particular features which are contributing for explaining the very thing. I have two things in mind. One is can we infer anything about the priority order of the features? And secondly, suppose there came any features and there are some dependence portion in it, like xk is dependent on xk prime, or maybe like
Yeah.
two are not completely independent. Can we have like, do we have any idea about this priority and independence?
Yeah. So actually, the thing is, later we'll see that to optimize an algorithm, we will use some kind of heuristic to determine the priority of importance of the features. Because you see, in an explanation, the more the sense is that the features in the explanation should somehow have more weight. They should be more important for that particular instance, right?
That's a very good and interesting question, Sulagna. But right now, this definition does not take into account the priorities. At all, okay. It just says, okay, these features are important. The rest are unimportant. That's all. Yeah, it's like 1 or 0. But that's a very good thing that if you could take into account the priority among these features, as Avik mentioned, you can exploit that to get much,
Better.
more efficient algorithms that they look into. But the definition does not take into account that.
Yeah.
So maybe that is one way you can improve this definition of explanation.
Yeah. So this is just a binary, whether it is in the explanation or it is not. That's all. Yeah. Yeah. So this is an example. So it's a simple DNN, as you can see. And okay, so can you tell me an explanation with a trivial explanation? Like, do you see any trivial explanation for any given instance based on the definition? Yeah. Do you see that? Yeah. Yeah, that's right. The whole feature set is the trivial explanation. Yeah.
Who are you? Oh, I see. Okay, good.
Yeah.
So, audience. Audience, good. That is right. Can you understand why you can just give the entire features, okay?
Yeah, just set all xi's to vi's, then that has to be the output class C, right? So that's a trivial explanation. So, but we are interested in smaller explanations actually, because that is not very informative. So in this example, so we have a classification instance, which is the input vector is this 1, 1, 1, and the output is 15, which corresponds to the class corresponding to this top node, whatever it is. It could be anything. There are 2 classes here. So we will assume, for the sake of simplicity, that the input values can take only 0 or 1 for the sake of simplicity. Now, yeah, so and we'll say that the top node corresponds to CT and the bottom node corresponds to CB, 2 classes, whatever it may be. And for this particular input instance, 1, 1, 1 and CT, we have this here. We want an explanation. That's the question here. So is this clear? Yeah. Okay. So now it turns out that the set V2, V1 and V2, which is a subset of all the three nodes here, we have three features here. So each input is corresponds to a feature. So this particular subset is an explanation for this instance, it turns out. How can we check that? Yeah. So to verify this, what we can do is the features which are not in the explanation, we'll set them arbitrarily to anything, right? And we'll check all those cases, whether it still classifies to CT or not. But in this example, there are only two cases because V3 can take only 0 or 1, right? So yeah, as you can see here, so what we have done is we have set the first two, which belongs to this subset, as the same as our input instance, 1, 1, 1. And we have varied the last one arbitrarily. In this case, just 2, 0 and 1. So in this case, of course, it's the same as our previous thing. So it gives 15, which corresponds to the top node because it's more than -4. We take the highest one. And in this case, we keep these two same as the input instance, but we have changed the last one. But we still get a 3 and 2 here, which means it still classifies to be CT. Yeah. So that actually proves that this indeed is an explanation. The subset V1 and V2 is indeed an explanation for our particular instance, which we took.
Any questions?
Is this clear?
Clear?
Example?
Okay, good.
Yeah. Okay. So yeah, recall this explanation definition. Now, how can we make this into a SAT or unsat query? Because we're going to use SAT solvers for this to verify this, right? So yeah, so we want this to be true, but since this is a for all universally quantified thing, what we'll do is we'll take the negation of it and check for unsat, right? That's how we do, because we want this to be valid. So and yeah, so this is the unsat check we're going to do. This is just the negation of this thing, like P implies Q, P and not Q. Yeah. So, and we want to check for the unsat of that particular formula. Now, we'll write this as a short abbreviation, a verification, DNN verification query, P and Q, where P, the precondition is just E equal to V, which corresponds to this thing here. This set of conjunctions, E equal to V. N is just our DNN. And here Q not C, this post condition corresponds to this thing here. That the classification is not C, something else. That's what abbreviates to this thing here, not C, Q not C. Yeah. So yeah, for our example, the query would be just, set x1 and x2 to be 1. And you get something like not CT. You get the output as not CT, which in this case can only be CB, but yeah. And the unsat query would be, yeah, so this is the DNN query form, and this is the unsat thing which we want to check. And of course, we'll also have to add that each xi can take values from their domains, which in this case is just 0 or 1. So, and it turns out that this will definitely give unsat. We have already checked that. So yeah. But we are interested in smaller explanations, of course, because we always have the trivial explanation, but that's not very informative. So so this is the definition of a minimal explanation. So basically it means that an explanation is minimal if no proper subset of it is an explanation. You can't remove anything. If you remove even one element, it will cease to be an explanation. So that's what it's codified here formally. So yeah, this is the definition for explanation. It has to be an explanation, and for any input in for any feature in E, there will always exist some input in our input space, such that you remove this feature from E and you keep the rest of them as same as V, you still get a misclassification. Is this definition clear? Yeah. Okay. So yeah, a minimum explanation is just a minimal explanation of smallest size. Now, you might have noticed that a minimal explanation need not be unique, neither a minimum explanation. So it has to be the smallest size, but there could be multiple minimum explanations of the same smallest size. Yeah. So, but we are okay with one of them. So So this is an example to demonstrate minimal explanation. So the earlier example we had actually turns out to be a
Yeah,
minimal
I think,
explanation.
I had just had one point in your previous slide. Okay, well, all of what you said is correct. Go to the previous slide.
Yeah.
So what does it mean to have, I guess, I mean, it's obvious that it does allow, the definition does allow the possibility of admitting several minimum explanations. So from a intuitive point of view, having multiple explanations is also possible. Okay, so there could be
Yeah.
different reasons why it is as per that definition it is coming
Yeah,
to that
yeah,
conclusion,
definitely, yeah.
although you might want not to be too many.
Yeah, that's
such
true.
minimum
Yeah.
explanation. Yeah.
Yeah. So yeah. So the earlier example which we had turns out to be a minimal explanation. So how can we check that? We just remove one feature and check whether it still gives an explanation. So so these two were in our explanation. So let's try to remove v1 from the explanation and see whether it still remains 1. So what we have done is we have removed this. Now this can take any value. So we set it as 0. This is the same as our input instance, and it gives like 3 and 0 here. So you can clearly see it misclassifies, right? Similarly, we try to remove v2, and we set the v1 as the same as our instance 1. But we change this to 0, but it still gives a misclassification here. It gives CB here. So that means that we can't remove any of the two from the explanation. They both have to be. So which corresponds to saying that this is a minimal explanation. But it's not the minimum. As we can see, V3 seems to be an explanation. Yeah, to check V3 is an explanation, we'll arbitrarily change these two. So in the first case, we kept these both as 0 and V3 the same as 1. So we get this 5 here, which corresponds to CT, the top node. We now keep this 1, keep this 0, we still get 9 and -3, still get the top one. We keep this 0 and do this one. So in all three, V3 just same. The rest we are varying arbitrarily. We still get this top class. So it seems that this is an explanation, and it is indeed the minimum because it's of size 1. There's no smaller explanation than that. So yeah.
Is that clear? So just pause.
That's clear? Or,
Yeah, any doubts? Yeah. Okay, go ahead.
yeah, please ask if you have anything. So so we want minimum explanation, right? That's what our goal is actually. So can you guys suggest a naive algorithm, whatever the stupidest algorithm to get a yeah, exactly, right.
Like take any subset, like guess any subset, and then check if the other things not included in the subset, take all possible values of 0, 1, 0.
Yeah. Basically, take any subset and encode it into a DNN verification query. Yeah.
And see if that is a
Unsat. Yeah. Right. That's right. So yeah. So
But you have to enumerate all subsets.
yeah, basically what we can do is we can enumerate all the subsets of the feature set starting from the lowest cardinality, because if we have smaller explanation, we'll get it faster, earlier. If we start from the lowest cardinality sets and we encode that into a DNN SAT query. So we enumerate all the things in increasing order of cardinality, and we encode this into this. And if this gives an unsat, that means S is an explanation, right? Is this clear? Yeah. And we just return that subset as an explanation. So, okay. But as you might have already noticed, this is insanely costly. Yeah. Because the inputs space for the SAT solver to scan is tremendous, because let's say there are M features, let's say, and you have just taken the singleton first one. Let's say they are 1 to M, and you have just taken this S to be singleton 1. Now you're only setting the first one to be the same as V. The rest M-1 features can take any arbitrary value from their own domains, right? So, but we are checking for unsat. That means the SAT solver has to travel all those input space before it can conclude that That's not an explanation, right? Sorry, that is an explanation. So yeah, so there are exponentially large SAT checkings. And of course, since you're enumerating all the subset of F, the feature set, that itself is exponential. There are, yeah, 2 to the power n, if n is the cardinality of F. So in worst case, if you have to loop through all those, you're gonna scan, like if you scan through all subsets, maybe you get an explanation very late. So you'll have to scan through exponentially many subsets in the worst case. So yeah, so we definitely want to optimize this. This won't work. So a more efficient but less precise algorithm. So yeah, so what we can do is, to make this more efficient, we can try with the whole feature set, and maybe try removing one at a time, because that will have like less less expensive SAT queries. But of course, as we go more into the, as we scan more features, the query will increase, the cost will increase. We'll see how. So what we'll do is, for each feature in F, initially the free variables are empty, and the whole feature set is our explanation initially. Now what we'll do is, we remove one feature at a time. We remove one feature and see whether this gives an unsat query, which that means that we see whether this thing after removing F gives an explanation. So yeah, so yeah, initially there's only one feature we have removed from this. So the others, we set it the same as V, so no need to check for SAT. So only one free variable is considered here, which the SAT solver has to scan through this features domain. But let's say this is unsat, which means that this set explanation minus F is an explanation. So this can be free, right? We add this to the free set. Now, in the next query, we set this to be explanation is F minus this thing, this one feature. So you can see, as we get further in this algorithm, we keep adding features to free. As long as they are free, they're not included in the explanation, we keep adding them to the free. We remove them from the explanation and check whether we can remove more, because we want to minimize the size of the explanation. So as time progresses, this SAT query actually increases exponentially, because in the first case, we just had only one free variable.
Don't do, yeah.
Yeah.
So first explain the algorithm, okay? Then
Yeah,
you
yeah.
explain efficiency and so on.
Yeah, that's what I'm saying.
First, did you get the thing? So you're removing feature one at a time, okay?
Yeah.
And that's also the number of SAT queries will be
Yeah, right.
just as many as the size of
In
the
the
thing.
the
So
size
that's
of
good.
3.
Now you say whatever you want to say.
Yeah,
Yeah.
this question.
Right.
That's right.
Minimum.
Yeah, that's exactly right. That I was going to make that point. So yeah, you're right. When we stop at an unsat, we have a minimal explanation when we stop this, but there's no guarantee it is minimum. Because yeah, okay, I'll explain that later. So yeah, now we can, as you can see, now let's say 2 features have been added to the free set. Now in this query, there are 2 free variables which can take arbitrarily many values in their particular in their respective domains. So as this increases, 3 free, 4 free, it's getting expensive for the SAT solver to scan through all those free variables, right? So that's why this increases a lot, in terms of efficiency.
But that comment generally applies to any unsat query. Okay, what he's saying is that the larger the, I mean, was that clear? So one important point is what Shubman said, that this is definitely efficient in terms of the number of SAT calls that it goes through, but it has no guarantee that it produces minimum.
Yeah.
But it does produce a minimal. What the point that he's making is that each SAT, it's an unsat call, the unsat is much harder generally if the set of things that it has to explore for all possible values is larger. Okay,
Yeah.
that is the point.
And in this case, that is the set free. Yeah. So like this gives us, but this definitely gives us an over approximation or an upper bound, as we know, because any minimal explanation is an upper bound for for a minimum explanation, right? So it gives a minimal explanation, which is an upper bound or an over approximation. So yeah, what is the worst case number of unsat queries needed? So the worst case number of unsat queries is the set of features, right? The cardinality of features. But each unsat query may be very costly as the free features get more, more features are included in free set. So yeah, so these are the
Those points
disadvantages.
you've already made. I think.
Yeah, I already
There's
mentioned
only
that.
one point. Did you understand why are we called this as an over approximation? What it is an over approximation of, Anuraj? Yeah, it is not minimum. So it includes the minimum. Is in that sense.
Yeah, it is a minimal, yeah, which is always an upper bound for the minimum.
Good.
Yeah, and we don't know how far from the minimum explanation we are actually. We don't have a lower bound for that, right? So like we can be very far from the minimum and still have a minimal explanation. So yeah, that's a negative point. Okay, so the outline for the rest of the talk is, so because of this thing, since this algorithm is not that efficient, we'll introduce the concept of contrastive examples, which will actually help to optimize our search. We'll see that. And yeah, that will show better optimizations to our this basic algorithm, which we saw just now. And we introduce bundles and we see some experimental results. So a contrastive example is a subset of features, the same as like how it was for the explanation case, but here, altering one or more features from the contrastive example subset will actually give a misclassification. So it's kind of a dual of our explanation thing. So you can see from the formula what we are doing is, so I'll first explain this. So you take all the features that are not in the contrastive example and you keep them the same as that in our classification instance. And you still get a misclassification for some input. So you'll always get one input for which, even if you keep all the features in the set other than the contrastive contrastive example subset, even if you keep all those the same as our classification instance V, you still get a misclassification. Is that clear? Like, is the definition clear? Or do you have a doubt? Like, it basically means that this is not enough for this thing to be classified as C.
That's
yeah. Even if you keep all these features in F minus C the same as our V, it's not enough. You'll still find some instance where this fails, where this misclassifies. That's what it means for that to be a contrastive example. So,
in other words,
I'll show with an example.
So I think another way to say is that these are the features that are important to misclassify it. Okay?
Yeah.
Explanations were saying these are the features that if you kept the same as in the original value, that it will classify it the same way. Okay? Whereas here it is saying what are these values for these features, if you changed what are needed to misclassify it. Okay?
Yeah.
There it was to classify it as C, misclassify.
No. Yeah, it need not be. So no, it definitely is not. Yeah.
But there'll be some lemmas. Okay. So if indeed it's not clear, he will go through some examples. Then it'll be it'll be a lot more clear.
So this is an example from our earlier example only. So this set here, the subset of features V2 and V3. This is a contrastive example because you keep the feature in F minus C, which is V1, the same as that in our classification instance 1. and you get some input value for which this misfires. Can you see that? Yeah. You get some, this is the input here. So there exists X, so this is the X here, for which you kept the feature in this set 1, but you still get a misclassification. This one, not produced. Is that now is it clear? Yeah. Okay. So and how can we check whether some whether the set is a contrastive example or not? We can do this with the SAT query. Just the previous thing, we do it as a SAT.
You had that point. I don't know. Maybe you have it in the later slide. About this adversarial attack. Maybe.
Yeah, it is there. It is there.
Okay.
Yeah. So so we can check for that, because since it's a SAT query, we just need one example of it.
So,
So we
Avik,
can
I
import
have
it into this
question.
SAT query, which is the same as the definition.
Yeah,
It's
Avik, I have a question. I'm not sure if you can hear me.
Please go ahead,
Yeah.
Madhukar. We can hear you.
Yeah. So I just asking that. So basically, if you take a contrastive example and if you take, the complement set, then it will intersect with every minimal explanation. Is it?
No, but that is not. It is not like it is the relationship between contrastive example and the other one is not complementary. Okay.
Yeah.
It is kind of a dual notion, but it is not complementary. I think the
So
relationship.
it may not intersect with minimal explanation if you take the complement.
No.
Yeah, it need not intersect.
It need not.
Okay.
So there, there will be, a lemma that he will put out that will clarify the relationship. Okay, a little bit later. Yeah.
Okay, sure. Yeah, carry on.
Is the complement of a contrastive example a minimal explanation?
No, not necessary. You can see in the previous example itself, the complement is just the first feature, right? Which is not a minimal explanation. V2 and V3 is in the contrastive example. Yeah. That's not necessary. Yeah, V1, 3 and minimal would be V1 and V2. Yeah.
I think that at least from the example side kind of illustrates the questions that Madhukar and Shubham had. But as to what the relationship between that is, it'll be there in the later slide.
We'll see that later. So this is the verification query for the SAT solver. And so we are interested in smaller contrastive examples because there is something such as called as the duality of minimal explanations and contrastive examples, which we want to exploit to compute minimal explanations. See, our goal was that only earlier. We had to introduce to compute that itself, to optimize that thing. So we'll see somehow these contrastive examples help in computing minimal explanations. So contrastive singleton is just a contrastive example of size 1. Basically, you change that thing and you can find an example where the classification misclassifies, it misfires basically. So now this is an example. This is crucial. So this could represent a specific pixel in an image. Contrastive singleton could represent a specific pixel, so such that you change that pixel, the classification changes. That is very important, right? Because that pixel should be preferable for an attack. If you change that pixel, the whole classification changes. So yeah, such singletons are used in one pixel attacks, where you change that one particular pixel and the whole classification is something else. So yeah, which may not be preferable. Yeah. So this is
in other words, I mean, singletons, you better not have singletons because they are susceptible for adversarial attack. Okay, or even small.
They are the most favorite spot for attacks by adversaries. Yeah. Now this is a lemma. Can you see that? Can you see why this should be true? Every contrastive singleton must be contained in all explanations. Can you see why this should hold? So it's actually very easy to prove, but the intuitive notion is that changing that particular singleton misclassifies. So somehow it should be in the explanation. It is contributing to the explanation of that or the classification. Yeah. So that's the intuitive notion. So there's a small argument with an example, and you can extend this to prove that actually. So suppose you have these three features and the contrastive singleton is F2, and you have have this as an explanation, F1 and F3, which does not contain the singleton. Now you have a contradiction because first thing follows from the definition of the contrastive singleton, and the second statement follows from the definition of an explanation. So yeah, do I have to explain this or is it okay? Yeah. Okay.
Go ahead. Yeah.
Yeah. So we'll also use the notion of contrastive pair, which is just contrastive example of size 2. And a minimal contrastive pair is a contrastive example of size 2 such that no proper subset of it is a contrastive singleton. Yeah. So it doesn't contain any contrastive singleton. If you remove one, it will not be a contrastive example anymore. So and henceforth, oh yeah, and this notion can be extended to minimal contrastive example of any size k, where you remove one element, you take any subset of size k minus 1, it won't be a contrastive example. So here on, whenever we refer to contrastive examples, we'll consider them as minimal only. Like we won't explicitly mention it's minimal. We are considering only the minimal ones. Okay. So some more lemmas. So yeah, this is the thing which I think you were looking for.
I think, yeah, Madhukar and Shubman you had. So this sheds some light on the relationship between contrastive examples.
Yeah, so every explanation should contain at least one element from every contrastive pair. This is the lemma. And like the proof is very similar to the previous, the proof of that singleton one. And this idea can be extended to any general case, which says that you have any contrastive example of size k. All explanations should contain at least one element from that. All explanations. Now, different explanations may contain different elements. That's a different thing. But yeah, there should be at least one which is included in all explanation from this set, contrastive example set.
So does that answer partially your thing? Yeah, that's the relationship.
So far, do you have any doubts? Yeah.
Just one moment, please.
So there can be a case where the contrastive example can be, I mean, the minimal contrastive example is size more than 2, right?
More than
2. Right?
Yeah, definitely. Yeah.
Then how can there be a contrastive pair? Like there is no notion of there is no contrastive pair.
No. This is contrastive pair. Here we are considering only 2, but I'm saying that this can be extended to any contrastive example of size k. Yeah.
Yeah, I mean, I'm trying to understand if a contrastive pair always exists.
A contrastive pair always exists.
So I'm considering contrastive pair means you're saying size 2, or you're generalizing to any size k here.
Yeah, contrastive pair means restricted.
This lemma says there will be a contrastive pair always, right?
No. Yeah, this is a conditional thing, right? If a contrastive pair exists, then at least one of them must be included in all explanations. Yeah.
If it exists, that's all.
Yeah. So, okay. So this is the lemma actually, which the paper has exploited to find minimal explanation. So a minimal hitting set of all contrastive examples constitute minimal explanations. So do you know what a hitting set is? It basically it is a set that intersects with every other set for a given class, and a minimal would be like no proper subset of it is a hitting set, and yeah.
Is that clear? So if you're given a set of sets, okay, a bunch of sets, a minimal hitting set of all those sets is the minimum set such that
it intersects with all the sets,
every other set. So it'll have at least one element. So that's why. Okay.
Yeah. And yeah, and this is very important. So the minimum hitting set of all contrastive examples is exactly the minimum explanation. So you take all the contrastive examples and you compute the minimum hitting set. Minimum hitting set is a minimal hitting set of the smallest size. Yeah. So now this is the lemma that we are that this paper has exploited to compute better approximations for
Yeah,
minimal.
this is somewhat related. I forgot. Sorry, I forgot your name. Huh? Surya, no? Yeah, yeah. Okay, so you see, that is what. So if you can get all contrastive examples, then you get the minimum.
Yeah. So like if you're interested of the proof of this thing, you can read this because it uses a lot of heavy first order machinery, which even I'm not very clear about. So yeah. Now, okay. So earlier we saw an over approximation for a minimum example, right? The earlier algorithm 2 we introduced that computes an over approximation. Yeah. So now we will look for an under approximation for a minimum explanation. Okay. So
So is what he means by an under approximation, is that clear? So an over approximation means it includes, it's an explanation that includes it. Under approximation is it's a subset of the
yeah,
minimum.
yeah, subset of the minimum explanation. Yeah. So which gives a lower bound on the size of a minimum explanation. So state of the art actually exploits this duality. Now, so what we'll do is, so what we can do is we can compute the contrastive examples. We can iteratively compute the contrastive examples and use their minimum hitting set as an under approximation. Now see, here's the thing. If we are able to somehow compute all contrastive examples and also compute their minimum hitting set, then we'll end up exactly with the minimum explanation, right? But that's not actually possible because, yeah, I mean, it's possible, but it's not feasible because, yeah, finding a minimum hitting set itself is empty complete. And if you were to enumerate all contrastive examples, then that's the same as enumerating all subsets of F, and you have to check for that, right? Because a contrastive example is a subset. So that itself can take exponential time. So we'll consider some subclasses of all contrastive examples that are easier to compute. Now, this is the thing I want you to understand. If we have all the contrastive examples and take their minimum hitting set, we'll end up with a minimum explanation. Let's say we don't take all the contrastive examples. We take some subclass of contrastive examples. And if we compute the minimum hitting set of that subclass, where we exclude some contrastive examples, what we will end up with can like, yeah, so. Yeah, right. That's right. So, which means that it is an under approximation. It is smaller than the minimum hitting set.
Romit just went ahead before I could raise to him. So I'll repeat his answer. Or you want to repeat it yourself? Yeah. So he just said that it was an under. He correctly answered it, an under approximation.
Yeah. Because you see, if you increase the number of contrastive examples, the element can only increase in the minimum hitting set. It can never decrease, right?
I think you made your point.
Yeah, that's the point. So yeah. Okay.
Fine.
So the approach to do this is explained in algorithm 3. So in this, we are only considering contrastive singletons and contrastive pairs, because after that, if you have triples, the cost on this would be very heavy. It would have 3 free variables. Yeah. So first what we'll do is we'll look out for all the contrastive singletons. How we can do that? We have seen the verification query earlier. We just check for the SAT of this thing. We remove this feature and check for the SAT. And we add that thing to the singleton if it gives a SAT. So
one point that I want to make, I mean, you have already made it, but I want to stress. A query, a check for explanation is an unsat query.
Yeah.
Whereas a check for contrastive example is a SAT query. Okay. So, sometimes these SAT queries, especially if there are a lot of SAT instances, they're much more, they're less expensive than unsat. And that's why this approach may converge faster in some cases. That's the reason.
Yeah. And similarly, we will take all the pairs, and of course, here we are only considering, minimal contrastive pairs. So we remove for all the singletons, all the pairs containing singletons. We don't take them. And for each pair in this pair set, we check this SAT query. And if it's SAT, then we add them to the pair set, which means it's a contrastive pair, basically. So we have computed all the singletons and the pairs. Now, and then what we'll do is, all the singletons, what would be the minimum hitting set of all singletons? Yeah, right, just the union. And is that clear for everyone? Yeah. And we want a minimum hitting set for all the pairs also. So that would translate to actually a minimum vertex cover problem. Basically, we want one from each, because we know every explanation would contain at least one. So we want one element from each pair. And we want the minimum of that. So we take the minimum vertex cover and we add that to our lower bound. So that's the idea. Okay. So yeah, so this is the, I think I have already explained, this is the bound we get on the minimum size of the minimum explanation. So we add the singletons, cardinality of singletons, and the pairs, the minimum hitting set of the pairs, and it is a lower bound or a under approximation of the actual minimum hitting set of all contrastive examples. Yeah. So now recall the upper bounding thread we had earlier, which actually tries to compute minimal explanations directly. And we have this lower bounding thread now. Now we can combine both of them to kind of, squeeze the minimum explanation between them. So that's what we're going to do. So this is an over approximation. So yeah. So now what we'll do is we'll combine both the two threads, the upper bounding thread and the lower bounding thread, how we'll do that is we'll run both of them in parallel. So, and this is the algorithm one we get for this. So it basically says run both of those things parallel, and these are the global variables that we'll use. Singletons are contrastive singletons, contrastive pairs, free variables used for the explanation thing, upper bound and lower bound for the minimum explanation size. Yeah. So this will give us an approximation ratio between the minimal explanation and an actual minimum explanation. So what we are doing is, here we are using a minimal explanation as an upper bound for the minimum explanation, the size of a minimal explanation as an upper bound, and the size of this minimum hitting set as a lower bound. And we're trying to make it come closer, and we'll know that, yeah, any question? Yeah. And we know that the minimum explanation will always lie in between those two upper and lower bounds. Yeah. So that ratio between the size will give us how far we are from the minimum explanation. So for instance, if the minimal explanation we have from the first algorithm, the algorithm 2, is of size 7, and the third algorithm which we saw earlier gave us a lower bound for 5, we know that we are only 7 by 5 times larger than the far away from the minimum explanation, right? Yeah. Okay. So
yeah, if you're lucky, then maybe the TUB algorithm will converge.
Yeah, right. That's right. But now we
not actually using the results of the lower bounding algorithm in returning the actual set at all. It's just to get the ratio.
Yeah, that's right. That's right.
Now, yes, that's a good observation. So that is one of the optimizations that
yeah.
later on.
As of
You're
now,
exactly right. Exactly
as of now, we only use it to get a minimum ratio. I mean, the minimum lower bound, basically. Yeah.
That's a good point, Rohit. I mean, I think, yes, you're not using that. You could use it to get better minimal explanation. But that's what
but yeah, we'll use it later.
You have to.
Yeah. So so we want to optimize algorithm 2, right? Because that's what gives us the minimal explanation. That we are using that to compute one. So how can we optimize that? Because you know already why we want to optimize this, because as the free feature set increases, the cost increases for the SAT solver to check and set. So to optimize this, we'll introduce 3 methods. First, I'll discuss 1 and 3 as per the paper. And both methods will help to remove stuff from going into free, because we want the free to not grow too much, right? That would be easier. So that would make things easier. So yeah. So the first method actually removes those features which will definitely be in the explanation. Hence, they need not be checked. Like they'll never be free, right? And the second method, the third method actually uses a heuristic to remove those features from the subspace that are very likely to be in the explanation. So it actually uses some kind of heuristic model to predict that these features are very likely to be in the explanation, and we remove that from the free, from going into free. So yeah, and method 2 uses binary search to eliminate some wasteful calls for a sorted feature list. We'll see what that means.
Yeah, I mean, here, Sulagna, the point that you mentioned is exploited here. If there is some way that you could somehow weight these features, okay, in the order of their significance, then you could try and use binary search, okay, to make it more efficient. Yeah. Okay, now that is outside the scope of this paper. He does not discuss that thing.
Yeah,
but he assumes there are.
Yeah, well, actually, they have used something called a heuristic model called LIME, LIME. That's the heuristic model they have used.
They do that. There are tools that can.
Yeah. So now let's see the algorithm which implements method 1. So we want to remove those features which we know for sure are in the explanation. We don't need to check them. So of course, first we can remove all the singletons. So what we'll do is we'll call the lower bounding thread which computes the singletons, contrastive singletons, if you recall, and we'll remove those features from our remaining feature set. So what is this remaining features? It is the set which we need to check for free, whether that feature would be included in the explanation or not. We are going to check for that. So from those remaining features which we need to check, we'll remove all the singletons because we know they have to be in the explanation by the lemma. And we'll also remove, we know that for each contrastive pair, there at least one would be in the explanation, right? So what we'll do is, first we'll check whether for a given feature f, we will check whether this query gives an unset or not. So if it gives an unset, that means this thing is an explanation, right? And this feature is free. And if this feature is free, let's say you have a contrastive pair which has this feature and another feature, let's say E comma F. And we know that this feature is free. What does that tell about E? That it must be included in the explanation, right? Because of the lemma. Yeah, am I making sense? Yeah.
One of the two has.
One of the two must be included. And we know this is not. This is free. So other one has to be in the explanation. So we will remove all those features to be checked from the remaining feature set, as we are very sure that they have to be in the explanation. So that's what this line does here. So delete all features in a pair with F from remaining features. Whatever features are in the pair, we'll remove that. And the pair we are getting from this lower bounding thread, because it gives us the contrastive pairs. Yeah. And this will help reduce the search space, quite much, because we are decreasing the size of remaining features which we need to scan. Yeah. Now the third method is local singleton search. So this, yeah. So yeah. So yeah, I'll try to explain that this may seem a bit hand wavy thing. So I'll try to explain as much as I can. So what this method does is it tries to remove all those features based on a heuristic hypothesis that if we have a feature that is not, that is free, that is in an explanation that is not free, the input values, near to that particular feature, which is a witness for that unset query. So what I mean is, yeah. So
I'll do that. I think what the assumption is that all the features that are potentially, I mean, a feature is in the explanation if there is not checking if it is something that goes outside. So you have to check if that is unsat query. Okay, a violation to the unsat query, it will become sat. That is a counterexample to unsat. So those are the values. The assumption is that those things that go into the thing, they're all are bunched together. Okay, and therefore uses the counterexample to that unsat query to get this.
Yeah. Yeah, so we use the counterexample, and the counterexample means that f has to be in the explanation. It cannot be free, right? Because unsat means free. So now, yeah, so we'll see that if there are other features which also violate this thing, which are close to this particular feature, and so if there is such a feature f dash, then it's very likely to be a contrastive singleton, which means it has to be in the explanation. If it is close to our counter example, you will see in the algorithm, and that we can remove from the from the remaining features which we need to check. So this is the algorithm for the local singleton search. So what it does is, this is our usual unsat check for whether f is in the explanation or not. So if this gives an unsat, which means f cannot be free, it has to be in the explanation. So we extract that particular counterexample for which this gives an unsat, and we check that for
for which it gives a sat.
Yeah, for which it gives a sat. Yeah, and we check, we extract that counterexample, and we check that you now, instead of v, we have set c here. Now we are checking whether the feature, the input is for this particular value, whether it misclassifies. And the heuristic assumption is that if c misfired for v and something else misfired for c, then it will also misfire for v. So those things, those input values which misclassify or misfire for a given instance tend to cluster together, right? So that's the heuristic assumption they are making. And if this is sat, which means that this feature also misclassifies, right? This gives an this sat thing. So this also has to be in the explanation. So we include them in the local singleton set, and we remove them from the features we are scanning. It's kind of uses a transitivity thing here. So okay, is it clear, or yeah, I'll move on.
As long as you got the gist of it, then I'll be happy. Yeah.
Yeah, I actually have an example also, but I think I can skip that.
You should skip that.
Yeah.
I think you should also skip the binary search algorithm. I know that.
Yeah, that I'll mention in 2 minutes. Yeah.
It's also experimental results, which.
Yeah, just 2 minutes. So basically, now we have, okay, I won't show the slides. I'll just say it. So we have some way to, give weights to each feature. Now, if we can sort the features in ascending order of importance, we note that the features which are at the end are more likely to be in the explanation. So now making a linear call would have a lot of wasteful things, because if we have a feature f which is in the next is not in an explanation, we know all the features to the left of it will also be not in the explanation, right? Because they are less important than that. So we'll skip those things. We'll do a binary search. We divide that point. And how do we check that? We check the point where the sat query flips from unsat to sat. That's the thing we do here instead of the usual binary search thing. So yeah, so I'll skip this. I have explained this. Now this is briefly about bundles. So basically now we group these features instead of taking each pixel at a time. We group these features as a set of features which are related to each other. Basically, this bundle kind of gives the sense of an ear, and like this gives the sense of a nose. That's the idea here, which makes the explanation more compact. And also it reduces the search space, because we are removing a bunch together instead of removing each at a time. And this is the formal definition. A bundle is just a subset of the features, and bundles, the set of all bundles, is a partitioning of the feature set in the bundles. So yeah. Now this is the definition of a bundle explanation. It's very similar to the previous one, but now we are just considering the union of features in the in our bundle sets, basically. Rest of the things are very same. So we'll use similar notions in our algorithm and etc. like minimum bundle explanations. Oh, this is a theorem which actually gives us the correctness that we can do this. So we'll use notions like bundle contrastive examples, bundle explanations, and etc. And we'll implement. They have implemented that in the algorithms also. So now we get into the experimental results part. So this graph gives us the average portion of features that were verified to be in the explanation. So this is the state of the art. I don't know if it's visible or not. I don't think it's visible. So this purple one is the state of the art, and this blue one is their contribution. So we can see that the feature space that they covered, that they scanned for, is quite more than this state of the art. And like these intermediate stages are the various optimizations that they have incurred. So this red one is without the singleton search. This green one is without the binary search, and the blue one includes all the three. So that improves the algorithm. And this one, so this experiment was done for the MNIST dataset, and they have constructed their own DNN for that. It's somewhat like 30 layers, 10 layers, and then 10 softmax layers, something like that in the paper.
And also, all their training sets examples are for digit recognition.
Yeah, MNIST. But they have also done it for fashion also, which they have included in the appendix.
I see.
Yeah. So this is the average explanation size that we get. We squeezed using the both upper bounding and lower bounding thread, and this is the size. And you can see that this is the method in the paper which gives the lowest size explanation, and this is the state of the art. And of course, these are the intermediate stages where you apply these optimization methods. Yeah. Now this is the graph which kind of over time tells how far we are from the minimum explanation. So as we can see, this is the lower bounding thread, this is the upper bounding one. So initially there's a steep increase because the SAT solver easily identifies all the contrastive singletons, only one scan. But as time increases, the cost increases for the SAT solver, so it gets slower and slower. Similarly for this, it gets slower as the free features increase. So yeah, and like there's a lot of room for improvement here, right? So and this is an example to demonstrate bundle. Like if you use bundle, this is the explanation we get, which is more compact than this. There's a it is more compact. I mean, you can see that. So yeah, and this is for the fashion MNIST, and the white pixels doesn't belong to the explanation. Yeah. So future work would be, first of all, better heuristics to optimize the algorithms to greater extent. And we can compare other explainability models with this one, and maybe combine both of the or one or more of them to even get a more comprehensible explanation. So that could be something we can do. And so this is the thing which sir told me to include. So if we used max SAT instead of the direct SAT one, what would be the impact on our provable guarantees for the minimum explanation? Yeah. Because max SAT makes it faster, but it gets less precise because it kind of approximates the SAT solving. Like it solves as many conjunctive clauses it can, not all of them.